First of all, I want to say thank you for the organizing committee. It's an honor to be here. It's your pleasure. Well, let's start. This quote is from my paper on SciM. Basically says that we are protein-based form of life, right? So it's well known from evolutionary reasons that geometry and function must be connected, right? There is a cost to be a certain shape. So somehow it must be connected to the protein function. We have some techniques to figure out protein geometry. This data is from Protein Data Bank. As you can see, NMR is the second one here with 11,000 entries. And here is the number of entries of NMR data in PDB Bank during the years. So it's still a very important technique. And another thing that we have learned from this previous presentation is that NMR does not give locations. Even what is given is a bunch of information, maybe incomplete, maybe imprecise information about distance. So it leads up to our optimization problem. I have a background on mathematics and computer science, so I'm more interested in algorithms. I see myself like a programmer than a mathematician, so I will talk more about how to implement this and how can we do smart code. So let's define the problem that we will face here. We are dealing with a distance geometry problem. We are given a graph, a simple graph, a distance function, and what we want to find is an embedding function x, such a way that the embedding satisfies a bunch of constraints. If we assume that there are some kind of order in the vertices, we can represent the data as an incomplete Euclidean distance matrix, and the output would be the locations. This problem is known to be an NP-hard problem. It can be reformulated as our optimization problem, global optimization. The problem with this approach is that the number of local minima is too large, so there is no hope the problem is not easy. As usually, the fact that the problem is NP-hard doesn't mean that all instances will be hard to solve. In fact, if we know all information, we can solve it in polynomial time. And if we assume a certain order, we can even reduce the number of operations. For instance, Dong and Vu have presented an algorithm that solves the same problem with the same amount of information using much less information. So what is behind this is that I call it the power of divide and conquer. If you have any method that is non-linear, and it's better to split the problem into small ones because the cost will be reduced. And when we impose a kind of order that allows us to build up one atom at a time, we will end up with a much less cost function. So order in this kind of problem is important. This is the message in this slide. So we will rephrase the problem as one problem where the order is given, so it makes the problem easier. So now we have our distance geometry problem, but we assume that we have also an order here that satisfies these two constraints. Now, one is each k plus 1 consecutive versus forms a clique. And the other one is a kind of non-degeneracy constraint. In 2D, this means that two consecutive points do not overlap. In 3D, it means that they are not collinear. And we can keep going. In terms of Euclidean distance matrix, we are dealing with this kind of distance matrix. We have the main diagonal is always 0, and the second one and third one, this is 3D, right? In 2D, I would have just the three main diagonals. We might have more information over here, right? This problem is interesting. But from the theoretical point of view, is a challenge because it's NP-hard. But it has a very interesting property. The one that Phil, in the morning said it's globally not rigid, right? But it's local rigidity. So I will show, it's quite easy to see, right? I will explain this in 2D. Let's say if I start putting x1 anywhere, could be the origin. Then because I have this edge here, this information, I have a circle. I can put the second point any place, anywhere over this cycle. I decide to put it here. Then because I have the distance between the vertices number 3, number 2, and 1, I have this 2 cycle. I can make an intersection. I will have 2 options here. And the things go on. For each possible position to number 3, I have 2 for number 4. And for each of them, okay, I should have 2 for 5. So this, the interesting point here is that if we have this kind of Euclidean distance matrix, the search space will be finite. It can be large, but it's finite. So some strategy that tries to enumerate the possibilities could be applied. Another important thing that this kind of graph have is, look at this. Imagine that here we don't have these 3 distances, but suppose that we know this one. If we don't have any more information, all of those realizations would be feasible. But if I have this one here, just 2 of them can be true. The reason is, suppose that this guy is right. The distance between this point and this one is right. Because this line is the line formed by the points that are the same distance from this point to this one. Because x1 does not belong to this line, if this guy is a solution, this cannot be a solution because the distance between this point and point 1 is different. So we can apply the same strategy here, and we will conclude that none of those other points are solution, except this one. So if I have one more distance, it defines not just the solution, but the entire component from 1 to 5. These 2 distances will be a function of this function, of this distance. So this is important because now we can somehow define independent components. In the case of Branch-and-Prune, in the literature, it's called symmetries. Let's suppose that we have our 2D again. The 3 main diagonals is now. I have this edge here, and I have this other one here. Because of this result, I know that just 2 of those points for 5 realizations, only 2 of them are actually solutions. So if I look here, this point, we define it as a unique solution here up to reflection, a unique solution for this sequence of points. And this other point here, we'll define a unique solution here up to reflection to this sequence here. And the interesting point is, if the intersection between those points has at most k points, so they will be independent. And the reason is that if you have more than k points in a k-dimensional space, they have a kind of chirality, some internal orientation. So I will show you here. Let's say that instead of 2, I have 3 points here. So the 3 points will be these yellow points here. For the green area, I will have this structure here end up with the green points here. And the other possibility, because I have 2, right? The other one would be this one. But they cannot be attached to the red one because it has an internal orientation here that's different from this one. It's a reflection, no? Right? So if in 2 dimensions, if I have an intersection with 3 points, I cannot bind the solutions. So this is important because by using this idea, just looking at the matrix, I can figure out how many solutions the problem will have. And even more, if I have one solution, I can build all the others just by using this reflection through this intersection here. Okay. One important question is, well, for defining this problem here, we did a lot of assumptions, right? I knew many information. And the question is these assumptions reasonable? Well, Carlile and others have proposed a kind of order it's a backbone of a protein. This order is a little bit awkward because you label some points twice. So for instance, this hydrogen is the number 12 and also the number 8 in the ordering. But if you assume this order and also that the length of the chemical bonds are now, and also the angles between two chemical bonds anyhow. And also another one is that the distance between two close hydrogen atoms also known with these three hypotheses. This actually will lead us to our other, that our theory about discretizing the search space, the symmetries will be valid. And Carlili yesterday said that we had a little debate in the last event between me and Leo. And yeah, it was nice. And it basically was, the problem was, like I said, I'm a guy from, I code. This is what I do. I code all day. And I was spending some time with Carlili making a postdoc there. And I had to implement this one algorithm to do this to a genetic graph. You give me a graph. I want to know if it has or no a reorder. And when I try to implement this, I end up with a polynomial code. I look the loops. I know that it was polynomial. Then I start to read the papers in order to understand what is the theory behind this. And in the paper, I saw that it should be NP-hard. But I know that my implementation was too naive to solve the problem NP is or not equal to P. Well, not the case. So that should be something wrong. Then so the consequences was that actually my code was right, but the paper was not right. The classification of the problem was not right. But at the time of the event, the proof was not clear. And I tried to present, and Leo was there, and we debate a lot. Yeah? But at the end, the closing case is that we published a paper recently about this, proving that the class of the problem is not NP-hard. Okay? What is the
Okay, you should explain it a little bit.
Okay.
It includes an NP-hard subclass, and so the whole class is NP-hard by inclusion. I explained it very poorly, actually. I explained it wrongly, that's true. But the problem is still NP-hard in its entirety, but it's one of those cases where for k equals 1, the problem is NP-hard because it becomes the Hamiltonian cycle.
Yep.
But for k greater than 1, it turns out to be polynomial. It's one of those cases. So it depends on k. So the entire problem, including k equals 1, is still NP-hard.
Yeah.
It's clear.
Yeah. So what is a reorder? We have the need to, the reorder, we have a graph. We want to know if it can or not be reordered in such a way that those properties that finite search space, and symmetry can be applied. So we have a function, we are looking for a function R that labels the nodes in such a way that the first nodes will be a clique, which is the final core that Phil talked earlier. And the other one is that you have a sequence of points, they must be our clique. And the last one is the awkward, is that if the points are consecutive, or we have our edge, or they are equal. This is basically the idea. No? So how do we prove this is a polynomial? To find such a order is a polynomial problem. I will explain the idea behind this proof in 2D case. So here the graph in 2D. We want to know if we can make a reorder here. The idea starts by building a new graph G prime in such a way that the vertices in G prime are cliques on k cliques, cliques with size k. In the 2D, the size of the clique will be 2. So this is the vertex in G prime. And the edge in G prime, there is an edge between this vertex and this one if the union of this set with this set is also a clique. So the vertices are cliques, and the edges are here if the union of the vertices are also cliques. So we can build this graph, and it turns out that the decision problem, if there is or not a reorder, is easy to solve if we have this graph. We just need to look if we can find a component of this graph whose the union of the vertices is the vertices of G. If we find this, we can solve the decision problem. So we create the G prime graph, then we look for a special component. Because create the G prime is cheap, it's polynomial. and also to check the component property is also cheap, we can actually solve the decision problem in polynomial time. And the other problem is that we decided if that is or not. Now we want a specific order. So the way to create a reorder from this graph is that we just pick any path that passes through vertices in such a way that the union of the vertices in the path must contain all vertices in the original graph. If we find a path and the union of those vertices is the entire graph, then we just split it. So let's say that I pick this order here. I put F, J, A, then I go here, pick C, E, C, B, D. This is the idea. So I will repeat. Well, I'm following this path here, right? Then I start here. The vertex here is F and G. So I put the F and G. Then I go to here. Here I have a new vertex A, I put here. Then I go to here. The new vertex is C, I put here. Then I go here, E. Then I come back. I could choose A or C. I choose C, put here. And then I go back to here. I collect B, and then here I collect D. Why this order is interesting? Well, because this point is different from these two, I knew that I can, and I know the distance between A, F, and G. I can discretize the position of A. If I look at C, I know the distance between C, A, and G, so I can also discretize the position of C, and so on. Here, because the two previous points are E and C, I know the distance through E, and the C to C is 0, so I can also discretize. So the discretization property is valid for this kind of order. What I...
I'm a little confused. So the vertices of this new graph are pairs for which you know distances?
Yes.
And you are looking essentially for a walk over some spanning tree.
Exactly. This is why this part of the problem is polynomial. Exactly. In the algorithm, exactly what I do. I make a spanning tree, look at any path there, then I have a solution. So it's also a polynomial. So in fact, this problem is easy and can be solved for k bigger than 1. We can solve it in polynomial time. So this was one of the contributions of this work. Now I will start to talk, so start to stress here. This is one of the contributions that I want to show. The other one is about, say, Phil.
So there's many orderings that you can do this way.
Yeah.
If you were try, do you know how many there are? Does it grow exponentially? I mean, is the trying to get them all orderings? Is that hard
easy?
or not?
Well, it's the number of spanning trees, right?
It's all walks on the span.
Walks on the spanning tree.
Yeah.
Yeah.
And
It's
it
a large
looks
number.
it looks like a large number.
Yeah.
But it's a question of whether he needs to find all of them or whether there's
No.
a subset.
No. Yeah. One is enough. No, I don't know if you have to find all of them, but in our case, you just need one of them to apply our.
There may be better ones than others.
Yeah, of the short one, maybe. No? Yeah. Okay. But there is one point to say here. If you have a more repeat, if you repeat the same point many times, it's not a problem because we have already fixed it in the previous. So it's a fake point, right? Now I will try to explain the branch-and-prune algorithm. Why I will try to explain it better. But the reason that I'm explaining this is because I've done improvement in this algorithm. So my version of this algorithm is much faster. So I need to explain why this is not so good idea and why can we improve it. So let's start by explaining how BP works. BP knows that the search space is a binary tree. So it starts to look at one branch at a time. And here the levels here are associated to the point that I'm actually locating. So first level, first point. Second level, second point. I'm in 2 decays. Then for node number 3, I have 2 options. Number 4, I will have 4 options, and so on. In the BP algorithm, we would start by putting the first point in the origin, could say. The second point we put in the appropriate distance. Then we go to this choice. Then 4. When I go to 5, I have a distance here. Look at, I know the distance between 1 and 5. And I also knew from the symmetries that just one of those should be the solution. Because the other one is in the symmetric side, the other side. So here, just one of those.
The fact that you have not made the edge 3, 4 orange in the right-hand side, this is just because you're not looking at the right-hand side.
Yeah, the idea here is the black ones will never be visited. This one could be, but will not also.
Just a minor point on the drawing itself. So it should at least be symmetric. And it's not. The colors are not symmetric, is it?
No, what is symmetrical here is the solution. The solution is symmetric. The green one means that the information that I need to get.
Okay, so you used the symmetry already to say I'm not looking at that.
Yeah. So what BP does, he starts from 1, 2, 3, 4. When he tried to locate 0.5 in that particular position, he look at the distance. Then he will see that it's wrong. So this is not the solution. Then this entire subgraph will never be visited because this is already wrong here. There's no way to fix by going down in this side of the tree. So this is for the idea. When we prune this, we go to the other side, this the position 6. Also, in my example, this is also infeasible. I prune it here, go back, and try 8. It's also infeasible. I prune here, go back to 7, 9, and then I find 10, 11, 12, all of them feasible. And look again, I know the distance between 8 and 5, so 5 is here. This distance is feasible. It could not, it might not be feasible, but it is in this case, in this example. Now I use the theory about reflections. I found one solution, right? The solution is 1, 2, 3, 7, 9, 10, 11, 12. If I have this solution, by using symmetry, I knew that reflection around the 4 and 5, 0, 4 and 5. If I made a reflection through these 2 points, 4 and 5, I will get another solution. So this size is also a solution.
But the BP has not explored it. You can
no, I don't need to explore.
Exactly, but then what is the meaning of the orange? I thought it was the thing that the BP explores.
I know, maybe overlapped. Okay. Here is the solution also represented by the orange.
All right. It means
so the number is the actual point that were visited. Okay. So here I know this is a solution, but I don't need to look for it. I can just build it, right? So based on this reflection, but I also have a reflection here between 1 and 2. So I can reflect this both solution to the other side, and I get more solution. This is the idea behind BP. So it explores all branches one at a time. It makes prune as soon as it can, and then if a solution is found, it creates the others just by flipping the appropriate portion of the points. What I call independent components. Now the improvement. How many? 15. Okay. Let's see. BP remembers its mistakes, right? Look here. When he prunes something, he will never do the same mistake again. He will not try to reach this point again. This is the idea behind prune, right? But it does not use the right choices that he learns during the process. I will give an example. Let's say I have a distance, and I'm trying to use a Branch-and-Prune algorithm. The green one, I have two. I know because of this that I have just 2 solutions here, 2 solutions here, and also 2 solutions here. If I consider just the dashed squared, right? If I use BP here, let's say from my example that the solutions are this one with this and this, or the flip, this one with this and this, are the solutions of the entire problem. What BP would do? He will generate this green one first, then the other green one, and the other the green. So this first, then, and when he put this point, he will realize that the solution is wrong, it's a mistake. Then we will need to make a backtrack in branch-and-pruning. So he will generate this, is wrong, the cost would be this. In the worst scenario, I made all numeration. I did this. Then, because it's wrong, I will set this to green. The cost to flip all points will be this one. but it's not a solution. Then I come back here, flip this one. Again, the cost is not a solution. Then I advance again the cost. So I have all this work here. But the point is, this is not necessary. It's not necessary to do this, to find the right solution. And the reason is, look, every time that we satisfy a constraint, we knew that the solution must be this one or the flip of the solution. There's no other solution. We don't need to recreate all the entire solution because there are just two of them. So every time that we satisfy a constraint, we consider this part of the problem as a solid body. So we just reflected this idea. So BP uses this when it tries to create the new solution given one, but it does not use this to create the first solution. This is the idea. So if I know this is a solid body, so I would not try all possibilities here. I would just flip all of them. And the cost to flip all of them would be the size of the component, not the 2 up to 2 to the power of the size of the component. So this reduces a lot the cost. But even this is not necessary. We can do one step further. Look, let's say that I have this part of the solution. This one is a component, a rigid component, and this one, the blue one, is also a rigid component. Everything that we're doing is just to fit the distance between this point and 1. 1 is 0. Just this, I'm looking for what is the right position of point 1. Because this is a solid body, and I knew that the only thing that I can do is reflection, I can apply the reflections only in the last point. I don't need to update all the structure to put the last point in the right position. Just apply the rotation, the reflections. So let's say that this is the first reflection, defines the reflection, and this is the other reflection. So I just need to apply this reflection in this point, and look, here I apply the green one in this point. And I already have this point in the right position if I move everything, but without doing this. So I look this distance to 2 to 0. If it is not right, I apply another reflection, let's say the blue one, and it ends up here. And then I look the distance between 0 and 4. Oh, it's not right, then I apply another reflection here. So all reflection needs to be applied only in the last point, not the structure. So instead of the size of components, the cost would be actually 1. So we went from 2 to the power of the size of the component to cost 1.
I'm not sure I understand what you mean.
Okay, I'll show you the picture, right?
Yes, so here you have Branch-and-Prune and it's gone up to position, say,
Yeah.
4.
Let's say that I start to do the Branch-and-Prune, so I end up here, right? But it's wrong. It's incorrect.
This is incorrect.
Incorrect. 1 is incorrect.
But if it's so you know that it's incorrect when you get there because you've got the distance between the first and the last atom.
Yeah.
All right.
So this first cost here is inevitable. I need to put it there. Okay, I put it there. So is it there? Now, because I consider this as a solid body, a rigid body, the only movement that's allowed to this guy is be reflected by this line. And because it's a solid body, I don't need to move all parts of it, just one point. I just need to reflect this guy through here. It is exactly position if I make the branch and put all those points here. It went up, and that's the same place.
I thought this was what we were doing when we analyzed those reflections. And then
No, it's not. No. I will show the numbers, the numerical results.
This is what I had in mind when I imagined the partial reflections. But
you don't use this to find the first solution.
I don't use it to find the first solution.
Yeah.
Okay.
Yeah.
But then after that, basically every other solution can be retrieved by an application.
For sure.
You can start with the last, or you can start with.
Yeah.
But then it's just a linear search over a spacer of reflection operator.
Perfect. Yes, exactly.
That's what I had in mind.
Yeah. But it's not your code.
Found one solution. This is before we found the solution.
It's to find the first solution.
The first solution.
No, you're trying to find the first solution.
Yeah. I'm using the symmetry to find the first one.
You'll find any solution, like the leftmost, And then you start looking for the right reflection?
Kind of.
Okay, but that is still a search that requires...
No, but it's not one solution. You don't have actually a solution, right? It's not a solution. It's feasible.
Okay.
It's a location, okay.
To try to go to the end.
Yeah.
Okay.
Yeah,
So the message here is that the cost can be reduced by considering this a solid body and just applying the rotation and reflection in the end. So as I said, I'm a programmer, so I made a code, right? So I made a code. I call the code SVP because I'm using symmetry. I also implement my version of VP, right? And I'm comparing with the standard implementation of VP, MDGP, implemented by Mukerino. So to be fair, right? So MDGP is implemented in C. I implemented my code in C++. It makes no big difference. I use this was the compiler. I use the same compiler flags, to be sure, and on my notebook, right? So I'm looking just for the first solution. But as I said, BP does not use symmetry to find the first solution, okay?
The first solution is feasible or infeasible?
No, the first real solution.
The first feasible solution?
Yeah.
Okay.
Yeah. So I stopped the running when I find the first feasible solution. I use default MDGP configuration, and I set up the max time as 1500 seconds, and how I generate the instance, right? They are artificial, but I download a PDB file, take just the backbone. In the backbone, it just considered only nitrogen and carbons. And a distance is included if I need to satisfy the order property. So if the difference between two vertices is less than 4, it is included. And the other one, if the distance between two carbons is less than 5 angstrom, is also included, right? So these are...
Wait a second. The distances, what precision do they have?
No, it's exact. Exact.
Yes. How many digits did you give them?
A lot of them.
Machine precision?
Yeah, maybe 16.
So these are very precise data?
Yeah, very precise data. So this is the kind of a distance I would get. These are the Euclidean distance matrix for one BDB, or one AFO, and one FHH. Okay? So here are the numbers. Let's see.
Be prepared.
Here the instance, number of atoms, number of edges. Here the time. Here the time. We're talking 10,000 faster. And here, to be sure that I'm solving the problem, right? I'm actually solving the problem. So when I look this number, it seemed to be too good to be true, right? Mm-hmm. That's some mistake. This is why I implement my own Branch-and-Prune. Because when I look the code from Mukerino, it's very easy to read the code. And it turns out when the code is too right to read, it's probably not performance oriented. Right? Most of the time it's that. So because I understood everything, I said, there's something wrong here. I will implement again. So then I implement it again. As you can see, my code is much faster than Mukerino code. But even in this case, the one with reflection is much faster.
So can you explain why? I mean, it's like it's 100 times faster
Yeah.
with reflections. Can you give us some intuition why the improvement is?
I think I try to get the numbers more or less here. We achieved this kind of course here by 1. We do not move all points, just the last one. This is why it should be so fast.
So the last, I mean, it depends on whether you have the last...
The last of each associated to each constraint, right? This is the idea.
Okay.
If I could just, of course, the symmetries of the P were discovered much after the PP algorithm. So the first version of the P algorithm were implemented without knowing the symmetries.
Yes.
Now we know a lot about symmetries.
But I thought that
why
Antonio-
not to exploit all of the three
No,
about
but I thought that
symmetry?
we were
No, it's
talking with Antonio that I had understood
I
that
know,
the
I
code
know,
had been
no,
updated.
yeah, but we use symmetries after we found the first solution.
Yeah.
Now we use symmetries to find the first solution. This is the big difference.
Yeah, I read the paper. I read the paper. In the paper, I read the paper in the code. The code is find one solution, then use the symmetry to find the others. This is the code. And the paper is the same. There's a if in the paper.
Yes.
If there is a solution,
Yes.
do this. If it's not, do branch-and-prune.
Okay.
And in the paper, there is a sentence that said, this is why we cannot use the symmetry before finding the first solution. That's a sentence right there. So the paper does not use symmetry, and the code also does not use symmetry.
So can you repeat again? Are you at the end? Are you at the end? Or
Yeah. So what would you want to see?
Okay.
Oh, this is the last one.
Yeah,
So
Do we have any
how
We
many?
have 1 minute and then we have questions.
So okay.
One more minute, you have 1 more minute to finish your talk. and then-
Okay, perfect. So I said that we'll show open problems. The open problem that I found here was now we can actually solve the problem. We can actually, if I show you the code, you'll see that the logic behind this symmetry is different. We do not fix one point at a time. We solve one edge at a time. This idea, because each edge defines a reflection. So we just focus on the edges, and there's well.
Duality in some sense.
So because of this, we focus on the edges. And the question is, the point is, we can start from any edge. We can start solving the problem in any order. We are free to choose the order. But for each order that you choose, you have a different cost. I don't know if there is or not an AP-hard problem to select the right sequence of edges. I don't know. I know that BP is not optimal. The order that BP chooses is not the optimal in terms of the minimal amount of work that needs to be done. And if you select the edges, the minimal edges in the size, it's not also optimal, because it depends on what you solved before. So it's a kind of find a path where the cost of the graph changes as soon as you make a choice. You select something, the cost changes. I don't know how to solve this problem. Okay, so this is the open problem. So I end up here. This is all.
Thank you so much. Okay, questions.
Questions? Do you have a question?
Yeah, well, I
Say.
still don't understand what you're doing to find the first solution.
Okay. Let's try here. Imagine that we are applying BP, right?
Yes.
So BP will find one solution from just considering this part of the problem. He will find a valid configuration, right? So let's say that the green one is the solution that BP would build just to this part of the problem. Okay. This portion of the problem is kind of independent of this one, right? Because the intersection is size 2, right? BP would also build a solution for this. Let's say this one. Okay. Then we go the next square here and find one solution. Let's say this one.
Okay, I get it. Okay.
Do you get? Okay.
agree?
But these 3 greens are no other solution to the type problem. Then I do reflections. This idea.
Any other questions? Yes.
Say.
So we also published a paper where we show that if you generate proteins sort of randomly according to a reasonable model,
Okay.
the probability of having symmetries beyond atom 4 is basically nothing.
Yeah.
So in your tests, evidently you do have symmetries.
Yeah.
So that
I
means
use
that
it as
they are well
Yeah.
exploited.
Yeah.
But that means that the random models that we use is probably not very good, or maybe. So how many proteins did you test? How many tests did you make? And did you choose them according to the presence of symmetries, or did you choose them randomly?
I select the size. I want 12, maybe the double,
So
then
this
double,
is a
double,
random
double.
choice of symmetries.
Yeah.
And they happen to have symmetries in. Sorry, this is a random choice of proteins, and they happen to have symmetries in.
Yeah.
That's encouraging.
Yeah.
So the only point is that then the distances that NMR provides are like 10
No.
to the 0, 10 to the 1, or 10 to the minus 1. So that's a real...
Yeah, it's a problem, yeah. Another is important here, just to finish. This the sign here, it means that after 500 seconds, they were not able to find a solution. But SBP found one in less than 1 second, so.
Well, did you push it to its limit? So what is the largest protein for which you had to wait 500 seconds?
I don't know.
Can you do it? Well,
Yeah,
now,
yeah,
can you
yeah,
do it?
yeah, yeah, for sure.
It's just
The problem will appear is precision before the size of the problem. Probably, yeah.
just a final remark. I love to put this guide together because it's a good example of how we can debate.
Let me add something.
This was really
Let me say one thing more.
This was very friendly.
Yeah. Well, it was friend to me last time. It's cool.
Guess I'm wondering does the nuclear norm come into any? I know it's just that nuclear norm would bring the rank down. Can you actually use nuclear norm instead of Branch-and-Prune to sort of do a parallel approach, or is it just a totally different way of solving this problem?
I could, yes. The Branch-and-Prune is a really general algorithm, so you can use any kind of distance or. The problem with Phil said this with any build-up algorithm is precision. When you try to solve large problems because you are solving one small one and use the solution to the next one, and there's no global attempt to reduce the error, you probably end up with some trash in the end. So we need to mix things. In the case here, there is another benefit. Because we do less operations, because we just flip the end points, the error should not accumulate so much. Because you're using different strategies here, just reflections. We are not solving a square system. We're not doing anything like this, just reflections. So should be better, I think. But I have no proof of this. Just all. Yeah.
Okay, one more question. One more.
So, you go.
Okay.
Oh, you have a question? Okay.
I was just wondering if you could use, so from NMR you can get distortion angles, if they can be used to rule out some of the symmetries in
Yeah. So to be honest with you, I'm from mathematics and computer science, so I start with this talk about NMR, but I have no contact with NMR at all. So I just pack a bunch of data, make matrix. Probably, if you can convert the information into distance, you can apply VP. But I've never actually put my hand on NMR data. And so we are the same, right?
Well,
Phil?
thank you so
Okay.
much. I don't think we have time for another.
Yeah,
We
okay.
should go for lunch. Yeah.
Yeah.
So let's thank the speaker again. So.